So welcome students. Now we are going to discuss about fundamental theorem of calculus. The idea is, does every continuous function f has an antiderivative? And if it does, what that f looks like. So here is the question. So suppose we are asking, suppose you're given a continuous function f of x on an interval, suppose on an interval I, then you're asking, does there exist a capital function f which is an antiderivative? What is the antiderivative? Antiderivative is a function f such that when you take f prime x, you get back f of x. For example, derivative of x square is 2x, right? Then antiderivative of 2x is what? Is x square. Yeah, rather, I mean, like you can have any constant here. In that case, antiderivative of 2x is x squared plus c. So that is easy. Now, what is the antiderivative of f of x, which is sine x over x? Yeah, this is slightly more difficult, more challenging. Difficult to get, right? However, notice the following. So this is the key result in calculus, which connects the integral with the derivative. Okay. So let f be a continuous function on AB. Then this function defined as integral a to x f of t dt. Let's call this function as g of x. Then the fundamental theorem of calculus tells you that this g of x is continuous on AB and differentiable on AB. So continuous on closed interval AB and differentiable on open interval AB. And not only that, g prime x equals to f of x. So your g of x is in some sense the antiderivative of what? Your function f of x. So if I want to read the same thing in a plain English, I can say that if I take derivative of this integral, so if I want to read the same thing, I can say derivative of an integral of a function. So with respect to what? Derivative is always taken with respect to some variable, with respect to its upper limit. Is the original function evaluated at the upper limit. So you have g of x. If you basically an f of x. So if you integrate f of x, you get g of x. And if you differentiate this, you get what? So this is a relation roughly, all right? So here with respect to upper limit, because lower limit is constant, that those things have to be taken into account. Right, so this is what roughly the idea behind the fundamental theorem of calculus is. We'll prove this later. However, let's apply the fundamental theorem of calculus on g of x here. So this is, so you get g prime x by fundamental theorem of calculus. You'll get g prime x equals to sine of x over x. Now, secondly, b, in that case, g prime of x is equal to, now note that this is not x, this is x squared. So you have to use the chain rule. So we get g prime x is same as d by dx of 0 to x squared sine t dt. This is same as f of x squared times d by dx of x squared, right? So in this case, you can see that this is going to be sine of x squared times derivative of x squared, which is 2x. Now, same way, can you do the part 3? So let's do C. So we have g of x, g prime of x is same as f of h of x multiplied by h prime of x. Again, the chain rule. Now let's try to do d. So can you try to do d, please? In d, you have to first break it into two parts, and then g of x, what we'll do is we'll break this into two parts. So minus 3x to e to the x of ln, sorry, minus 3x to 0, ln of 1 plus t squared dt plus 0 to e to the x of ln of 1 plus t squared dt. Now, when you flip the limits of integration, you will get a minus sign. So 0 to minus 3x with a minus sign, ln of 1 plus t squared dt plus 0 to e to the x of ln of 1 plus t squared dt. Now you can take the derivative. There is no derivative taken yet. So g prime x is going to be, using fundamental theorem of calculus, you will substitute minus 3x inside. So minus remains as it is, ln of 1 plus minus 3x the whole square multiplied by dx of minus 3x, chain rule, plus ln of 1 plus e to the x the whole square times dx of e to the x. So this is going to be minus ln of 1 plus 9x squared times minus 3. So I can basically make it here plus 3 plus ln of e to the x, the whole square is going to be e to the power. So 1 plus e to the power 2x times derivative of e to the x, which is e. So this is what g prime x is. All right, so now next result is the result which helps you on how to compute the integral using antiderivative, right? So we, until now, we have computed this using Riemann sum or limit of Riemann sum, but now this will help us to compute using the antiderivative. So what does it tells us? It tells us if we have an integral a to b fx dx, then this is same as f of b minus f of a, where f is any antiderivative of f. Okay. So the proof of this is pretty straightforward. It relies on fundamental theorem of calculus 1. So let's take g of x equals to a to x f of t dt. Now note that g prime x equals to f of x, right? This is the fundamental theorem of calculus 1, FTC 1. Therefore, g of x is an antiderivative, isn't it? G of x is an antiderivative of what? Of f of x. So let f of x be any antiderivative, then f of x is any antiderivative, then we know that f of x is going to be g of x plus some constant c. Yeah. So this was shown in calculus 1, right? So now if we have, so if x equals to a, we have what? So now let's look at this side here. So if x equals to a, we get what? F of a equals to g of a plus c. And if you look at f of b, that is going to be g of b plus c. So f of b minus f of a is going to be g of b plus c minus g of a minus c, because that is what f of a is. This cancels out. You have g of b minus g of a. What is my g? G of b is integral a to b f of what? F of t dt. What is g of a? G of a is a to a g of x dt. This is 0, right? Because the point a to a gx dx is 0, or g of t dt. Let's use t. So this is what we get. So therefore, integral, so you see, you have proved your result. F of t integral a to b dt is what? Is f of b minus f of a. Now, what is the notation? The notation is the following. We use the following notation. So f of b minus f of a can be written in short as f of x to b, or we can write it as f of x to b. This means that it is substitute the upper limit first minus substitute the lower limit. Okay. So now that will help us to do the following problems. So let's do the first problem now. Integral 0 to 1 x dx. So now, first of all of them are definite integrals. So we are going to get a number for all of them, right? So a, we get integral 0 to 1 x dx. Now, what is an antiderivative of x? It's x squared by 2. 0 to 1, which is going to be 1 by 2 minus 0 by 2, or 1 squared by 2 minus 0 squared by 2, which is 1 by 2. Yeah, note that, recall, antiderivative of x to the n is what? Is x to the n plus 1 divided by n plus 1 plus c if n was not minus 1, and is ln of absolute value of x plus c if n was minus 1. Yeah, you would have seen that in calculus. So let's look at b. Again, 2 to 3 e to the x dx. Antiderivative of this guy, e to the x, is e to the x. Again, 2 to 3. So we get e to the, substitute the upper limit minus substituting the lower limit, which is e cubed minus e squared. Okay, you can find the value, but the finding value is not important. This is good enough as an answer. C, 0 to pi sine x dx. Again, antiderivative of sine is minus cosine. So minus cosine x, 0 to pi. Then substitute the upper limit. So minus cos of pi minus cos of 0. Cos of pi is minus 1. So minus of minus 1 is plus 1. So if you want, I can write it minus 1 minus of minus 1, because cos 0 is 1. So you get 1 plus 1, which is 2. All right. Now, let's look at D. So 0 to 1 dx of 1 plus x squared. Now, antiderivative of 1 upon 1 plus x squared is tan inverse of x, 0 to 1. That is going to be tan inverse of 1 minus tan inverse of 0. And tan inverse of 1 is pi by 4. Tan inverse of 0 is 0. So the answer is pi by 4. So this is how you compute the antiderivative. Now recall, we did this problem in the last lecture. We had 0 to 2 of x squared minus x dx, right? Now you can do this directly using antiderivative. So we have x cubed by 3 minus x squared by 2, 0 to 2 That is going to be 2 cubed by 3 minus 2 square by 2, which is 8 by 3 minus 2, which is going to be 8 minus 6, which is 2 by 3, which was the same as the answer we got last time using the Riemann sum. Okay, so this is the way, this is a bridge which we built between what? The antiderivative and definite integral. So let's do another problem. Now, this is an interesting problem. So let's try to do, let f of x be this function and g of x be 0 to x f of t dt. Now find an expression for g of x which is similar to f of x. All right, so let's try to do this problem. So can you do this problem, please? So you can break it into few pieces. So now what we'll do is the following. We'll break the function part by part. And so part A, we'll find an expression for g of x. So f of x, so let's break it part by part. So if x is less than 0, then g of x is simply 0 to x of f of t dt. But in that range, if x is less than 0, 0 to x, in that region, your function is simply defined as 0. So 0 to x of 0 dt. And that is going to be 0, right? Because it's an integration of area under the function 0. Now, if you have your x is between 0 and 1, in that case, your g of x is going to be 0 to x f of t dt. And you get what? You get 0 to x. Now, what is the definition of your function 0 to 1? In that part, it is given by simply x. So if f of x is x, so f of t is going to be t dt. And that is going to be t squared by 2. That's the antiderivative of this, 0 to x. Then you substitute the upper limit minus the lower limit. So this is what you get. Now, if your x is between, so again, integral of f is a piecewise function, so it's very likely that integral will also be a piecewise function. Now let's consider the case when x is bigger than 1 and less than equal to 2. In that case, we'll have g of x. So first of all, g of x is integral 0 to x, right? So now we have to break it into two parts. So first part is going to be 0 to 1 f of t dt plus 1 to x f of t dt. Right? You have to break it into these parts. So this is going to be 0 to 1 f of t is similarly t dt, right? That's what in this range 0 to 1 your function is defined as x plus what? 1 to x. Now what is the definition of function from 1 onwards? 1 to 2, the definition of function is 2 minus x. So we'll write 2 minus x. Sorry, we are doing with a dt, so it will be 2 minus t dt. Now the first part is easy. You can see that this is going to be t squared by 2, 0 to 1, plus this is going to be 2t minus t squared by 2, 1 to x. And then when you substitute, you will get half plus, when you substitute x, what do you get? 2x minus x squared by 2 when you substitute the lower limit, which is 2, so minus 2 plus 1 by 2, right? So that is going to be half plus half is 1, minus 2 is going to be minus 1. So minus 1. Then we have plus 2x as it is, minus x squared by 2. Okay, so this is your g of x when x is between 1 and 2. Now later on, if x is bigger than 2, then your g of x is going to be 0 to x, again, f of t dt. Now we have to break it into parts. So this is going to be 0 to 1 plus what? 1 to 2 and then we'll have 2 to x f of t dt. Now we have already done this computation. So this is going to be half, already done before. 1 to 2 of 2 minus t dt plus 2 to x. In this case, after 2 also the function is defined by 0. So this is going to be what? 0 dt. So the answer is going to be half plus what? 2 minus t. So we get 2t minus t squared by 2, 1 to 2. So we get half plus 2t, so 4 minus 4 by 2, so 2 minus of, when you substitute lower limit, 2 minus 1 by 2. And that can be simplified to 1 half, so I can break it out, half plus 4 minus 4 plus half, which is going to be 1. So this is how my g of x looks like. So let me write down g of x as a piecewise function. So g of x can be seen as, let's see. So before, so if x is less than 0, then it's constant 0 function. If x is between what? If x is between 1 and 2, then it's x squared by 2. So it's x squared by 2 if x is between 1 and 2. Right? Oh, sorry. X is between 0 and 2, right? 0 and 1. My bad. So 0 and 1. And 1. Now, and the other part is, it's what? It's this thing, minus 1 by 2, minus 1 plus 2x minus half x squared. If x is bigger than 1 and less than equal to 2, and after that it is constant 1. So this is the function g of x.